Hello, and welcome to the next video in our series. This is the Essential Skills for Physical Science series, practicing those skills which will help you with Paper 1, the physics paper. I'm Dr. Derek Fish, Director of the Unizulu Science Centre at the University of Zululand. This is video 6.7, continuing with equations and looking especially at the equations that have to do with electrostatics. You'll find it on pages 58 to 61 in your booklets. But before we get to page 58, as always, let's turn back to page 3. Remember, in my bottom right-hand corner, you can always see the page number, so you'll know where to follow in the books. So just to locate this video in the booklet and in the curriculum, we're looking at the equation section. Remember, this is essential skills. We've looked at graphs, free body diagrams. We're looking extensively at equations. Then we look at multiple choice and ratio questions. To expand the equation section, we're looking specifically at the equations to do with electrostatics, and that governs question 7 in paper 1. Comment from the examiner in the yellow box here: learners still cannot work with scientific equations or formulae. So let's make sure that at the end of this video we can do. Turning to page 4, where does electrostatics fit into the curriculum? Obviously under the electricity and magnetism section. And in fact, this is not a matric section. Electrostatics was introduced in grade 10, and then you did some more in grade 11, where you looked especially at Coulomb's law and electric fields. So on page 5, please heed the warning that grade 10 and 11 work is important. And this is probably the biggest section of grade 11 work, which is examinable at the end of grade 12. Again, the examiner's comment: grade 10 and 11 work is poorly understood, and this work should be integrated with the work done in grade 12. So please don't forget, there's a lot of electricity from question 7 and question 8, which are carried through from grade 11 and 10. This is usually quite a long question. Question 7 is the electrostatics question, and on average over the last 3 exam papers, it has averaged 18 marks. The second longest question of the long questions, obviously multiple choice, is always 20 marks. 18 marks is 12%, and that can make the difference between 29% and 41%. So it's a really important question, which we need to prepare well for. So looking at the last 3 exam papers, November 2018, 2019, and 2020, this is a snapshot of what the questions were covering. And this question always has 2 parts to it, being a longer question. In 2018, there was a question on charge conservation, followed by a question on Coulomb's law and electric fields. 2019, again, Coulomb's law involving a free body diagram and a triangle of forces, and then an electric field calculation. 2020, again, Coulomb's law and electric fields, and then a calculation involving 3 charges and Coulomb's law. What about skills? On page 5, well, you'll see we need just about all the skills. We need to understand models in science because, of course, the atomic model is held together by Coulomb forces. Scientific notation is important because the Coulomb is a very large unit of charge, and we'll normally work in microcoulombs, nanocoulombs, or picocoulombs. You need to be able to work with those metric prefixes. You need to be able to convert units to SI units. You'll often have to change the subject of a formula to solve an equation. You will need trigonometry skills and angles, as you saw in those questions. Often you have a charge hanging from a thread at an angle which has to be calculated. Fractions and ratios as well, direct and inverse proportion, and constants like K for Coulomb's law. So all of these skills are very important. And again, the examiner's comment that a severe lack of skills was evident when marking the matric paper. These constituted mathematical skills, conceptual understanding, and integration of topics. Also free body diagrams, graphs, and equations. Now, please note that free body diagrams, which were dealt with in video 5, are quite often asked in question 7 as well. So maybe it's a good time to look back over that work as well. So as with all these equations videos, let's start by looking at the basic theory. Please remember, this is not a content video, and so we're just going to give a brief overview of the theory. Please consult your notes, your textbook, and your teacher to get the full story. We're going to go over the theory by looking at 4 excellent simulations from PHET. First of all, this one called John Travoltage. Then we're going to look at balloons and static electricity, and then Coulomb's law, and finally charges and fields. Now, all of these have been given to you teachers in your teacher packs, so please make use of them. You'll get much more out of them if you manipulate them yourselves and play with them than just watching what I'm going to do with them. Let's start with the basic idea of what charge is by looking at John Travoltage. Now, normally when you walk across a room and touch a doorknob, you don't expect anything to happen. But if maybe it's very dry and your feet have scraped across a carpet, there could be some buildup of charge. And in that case, when your finger gets close to the doorknob, you can get a shock like that. Now, this is called charging by friction. So let's look at what happens again. As the foot rubs on the carpet, electrons are rubbed off the carpet and onto the foot, and they distribute themselves around the body of John Travoltage. If the charge buildup is too big, you'll find he doesn't even need to bring his finger close to the doorknob. Let's see what happens. And you can see what happens. So this is charging by friction, and this is static electricity because the current only flows when it goes from the finger to the doorknob. Another experience I'm sure you've all had is that if you take a balloon and rub it on something like a jersey, it becomes charged and then it will stick to the jersey. It will also stick to the wall on the other side. Now let's try to get an idea of what's happening here. And we can ask PHET to show us all the charges. We see that the balloon has acquired a negative charge, and the jersey's become positive because you can see that electrons are being rubbed from the jersey onto the balloon. Now notice this is a separation of charge. The jersey becomes positive, the balloon becomes negative, and opposite charges attract each other just like that. How is it attracted to the wall? Well, what you can see is we get a temporary induced charge. The electrons are repelled, and for a while there's an induced positive charge when the balloon's there, but if we take the balloon away, then the wall goes back to being neutral again. Let's start again so we can see what happens. Everything is balanced with equal numbers of positive and negative charges, but as we rub the balloon on the jersey, you can see the negative charges, the electrons are transferred from the jersey to the balloon. The balloon acquires a net negative charge, and it's attracted to the jersey, and it's attracted to the wall. Let's see what happens if we have 2 balloons. Now, at the moment, the 2 balloons are both neutral, but let's rub the green balloon a little bit on the jersey so it becomes a bit negative. Let's also rub the yellow balloon so it also becomes negative, and you'll see we'll have 2 balloons that then repel each other. Because they both have a negative charge, they're pushed apart. So this is static electricity, and it's acquired by friction, by physically rubbing electrons off the jersey and onto the balloons. That leaves the jersey with an excess of positive charge and the balloons with an excess of negative charge. So that's just a very simple reminder of the basics of electrostatics. We will look at Coulomb's law and electric fields, but we'll look at them at the same time as we consider the equations related to them. Please remember to revise this section thoroughly from your notes with your teachers and from your textbook. So let's move on to look at the equations and variables associated with electrostatics, because that is the aim of section 6 of this video series. Now remember, with all problems across the different content areas, we will use the progress method for problem solving. This was explained very carefully in video 6.1, and you'll find it on page 37 in your booklets. Just a reminder for electrostatics, a picture often helps, particularly when you have multiple charges and angles. Check carefully what is required. Are you being asked for a charge, for a potential, for an electric field strength? And look out for what is obvious. Make sure you check carefully what is given and the units it's given in. You'll often find micro or picocoulombs which have to be converted. And then simply relate what is given to what is required by choosing the correct equation. Once you've got that, you have only to substitute values in and to solve. Now, to find the equation, of course, we go to our data sheets. On page 39, your second page of data sheets at the top, you have the electrostatics equations, 5 equations related to question 7. Please don't confuse them with the electric circuits and internal resistance equations, which are underneath that. Very important to understand which equation is which and when to use it. For example, there are 2 different equations for electric field strength, and you need to know when to use the top one and when to use the bottom one. Now, of course, this all starts with understanding the variables, and we're now on page 58 in your booklets, and we're looking particularly at electrostatics theory and equations. In the equations, we've got 7 variables and 2 constants. Now, there's some old friends which I've put in black, like force. It's often called Fe for the electrostatic force, is measured in newtons. But there are now some new variables that you might not be familiar with, which I've put in red. Q stands for charge, or it can be a small q, that's measured in coulomb. Because newtons and coulomb were named after famous scientists, they have capital letters. R is distance apart in meters. We're very familiar with that. And you'll see that the Coulomb equation looks very much like Newton's gravitational law equation. Then again, a new one, electric field strength, is measured in newtons per coulomb because it's force divided by charge. And V, potential difference, in volts. And then again, we're familiar with work in joules, and N is just a number, and it's quite often the number of electrons. When something gets charged, it can only get charged by adding or taking away whole numbers of electrons. We can't split the electrons. So sometimes you're asked to calculate this. Now, to do this, you'll need these 2 constants. Coulomb's constant, 9 times 10 to the 9 Newton meter squared per coulomb squared. And the charge on the electron, sometimes also written as Q small e, is minus 1.6. It's a negative charge times 10 to the minus 19 coulombs. And when you look at those in scientific notation, it might not be immediately clear that Coulomb's constant is a very big number and the charge on the electron is a very small number. We look at constants on page 40. You remember in 6.1, we suggested that these are the questions where these constants will come up. And the last 3 constants, including also the electron mass, although it's not in the equations, could come up in question 7. And I wrote out the constants for you. Let's just look at the electrostatics one. K, 9 times 10 to the 9, is actually 9 billion, 9,000 million. It's a very big number. The charge on the electron, you can see, is an extremely small number because the exponent is minus 19. And then ME, which is the mass of the electron, is also, in fact, it's an even smaller number because the exponent is minus 31. So just be aware of the differences between those numbers, but obviously don't try to remember the numbers, just take them from the table and make sure you can do scientific notation correctly, particularly with positive exponents and negative exponents. Now, to investigate Coulomb's law a little bit further, we're going to look at this great PHET simulation on Coulomb's law, remembering that this is the basic structure of Coulomb's law. The electrostatic force is K, the constant we've just talked about, times Q1, the charge on the blue charge, Q2, the charge on the red charge, divided by the square of the distance between them. And you'll remember this as being very familiar from Newton's law of gravitation. We just change the charges to masses, but it has the same structure. So here we are in the PHET simulation called Coulomb's law. As always, encourage teachers to use it from your teacher's pack and explore it. Here we have 2 charges, And the people there are showing the fact that there's a force between the charges. The moment we have a blue charge which is negative and a red charge which is positive, so they're being pulled closer together. Now the forces are indicated numerically and also by arrows. Please notice the magnitude of the two forces is the same, and the arrows show that the direction is different. Now you'll see as we move the charges, those forces will change. And we can look at the forces by looking at the size of the number and also by the length of the arrow. Now let's start with a simple one, the effect of changing the charge. The charge one is -4 microcoulombs. If I make it more negative, can you see that the force increases? You can see the arrows increase in length and the numbers go up. So clearly the force exerted by Q1 on Q2 or by Q2 on Q1, because they're equal and opposite, is directly proportional to the size of the charge on Q1. Same for Q2, if I make it more positive, again, from 8 to 10, the force increases. If I make it smaller, the force gets smaller. If I make it 0, then there's no force. And if I make it negative, now you can see the people are struggling to hold the charges together because the charges are trying to push apart. Okay, so let's go back to where it was. Now, what about the distance? And you can see the distance greatly affects the force. If I bring them closer together, the forces very quickly get very large. If I take them far apart, they very quickly get very small. And this is the effect of having a term 1/r² in Coulomb's equation. But let's do a rough calculation. You can see the force is about 800 newtons. Don't worry about the exact detail. And you can see the distance between them is about 2 centimeters. Now let's double the distance from 2 centimeters to about 4 centimeters. And you can see now the force is about 200. So it went from 800 to 200. So it was divided by 4 when the distance was multiplied by 2. Now these sort of calculations are covered very carefully in video 7 on ratio questions and multiple choice. And I encourage you to look at that. I hope that was a useful reminder on Coulomb's law, which you did in grade 11. Now, a good way to get practice with Coulomb's law is on page 67 in your book. This is part of video 7 on ratio questions and multiple choice. And this equation often comes up in multiple choice with a question which says there's a force F exerted by one charge on the other. Something is changed, maybe one charge is doubled, one charge is halved, the distance is changed, or a combination. What will be the new force in terms of the original force? Now, on page 67, there's a table at the bottom of the page. There's an exercise for you to do, and this is done in video 7, and the answers are given. I want to refer you to that because it'll give you good practice with Coulomb's law. Back to page 58. There's some points to note on Coulomb's law, and I think it's important for us to consider these points because they'll affect how we understand and how we use the law. First point, F is a vector and must be given a direction. You can see F is expressed with arrows. Now, you can normally just say towards or away or left or right or east or west. That's fine. We're usually just working with one-dimensional situations, but there have been some questions with two-dimensional arrangements of charges. Secondly, the forces experienced by the charges are equal and opposite. So F1 as a vector will be equal to minus F2. In either of these cases, they will be equal in magnitude and opposite in direction. And Newton's third law of motion says that has to be true. Now, the main difference between the electrostatic force and the gravitational force is that gravity always attracts. Imagine if it didn't, whereas electrostatic forces can be attractive or repulsive. So point number 3 tells us like charges repel. So two positive charges repel each other, and the force you calculate will be positive. Unlike charges attract, like a positive and a negative, and the force you calculate will be negative. Please remember that Coulomb is an extremely large unit of charge. A charge of 1 Coulomb is very unlikely in nature, and we will usually work in microcoulombs. That's a millionth of a Coulomb. nanocoulombs, a billionth of a coulomb, or even picocoulombs, 10 to minus 12 coulomb. And notice this important point 6. The Coulomb force is responsible for all chemical bonds and literally holds the world together. There would be no chemistry without the Coulomb force. So just to illustrate this a bit, we're still busy with page 58, but you won't see this in your book. So if you just look within an atom, what keeps the electrons from flying away? Well, it's the electrostatic force of attraction between the negative electrons and the positive protons, which are bound up in the nucleus. What holds different atoms together in bonding? Well, in ionic bonding, covalent, metallic, or even intermolecular bonding, it's an electrostatic attraction between the nucleus and the electrons. And so electrons are sometimes transferred, they're shared with covalent, or they're delocalized with a metallic bonding. Intermolecular forces are also Coulomb forces. And if you look at ion dipole forces, hydrogen bonds, all the other types of forces, they're based on the fact that one molecule has a net positive charge and the other molecule a net negative charge, or at least the parts that approach each other. And in fact, the fact that atoms bond together at all is an interplay between the attractive and repulsive forces. But just think, if there were only attractive forces, they would keep on getting closer and closer. And you might be wondering, apart from the attractive Coulomb forces, when do we see repulsive forces? Well, this wonderful simulation from PHET called Atomic Interactions talks about the fact that you have attractive van der Waals forces, which are slightly more long range, and then repulsive forces as the electron clouds start to overlap. So here we are inside the PHET app called Atomic Interactions. And as always, I encourage you to try it for yourself. It's in your teacher pack. So we have two neon atoms, and you can see at the moment the potential energy for the interaction is at its lowest point. If I push them closer, it will go higher because of repulsion. And if I pull them further apart, it will also go higher. And that is what leads to this comfortable lowest point of potential energy. Now, it makes more sense if we switch on the forces so we can see them. Now, there are attractive forces, van der Waals forces, and repulsive forces that are very short range and only come in when the electron clouds actually overlap. So as I bring the two closer, can you see about here, we start seeing those attractive forces, but also the electron clouds have overlapped. So we also see the repulsive forces. At the moment, the forces are balanced. So that's a comfortable state of minimum energy. And if I bring them closer, then the repulsive forces definitely take over. So they will be pushed apart like that. Let's consider it for oxygen. Now, oxygen has a much deeper energy well here. Let me change the scale of the graph. And that's why two oxygen atoms become very tightly bound. As they approach each other, you can see the attractive forces there, the orange arrows. Once the electron clouds overlap, we start getting repulsive forces, which are the pink arrows. And these forces are very large. So you get to this point where those forces are just balanced. They've actually gone off the screen. They're so large. And if we take the oxygen atoms any closer, then the pink repulsive forces will actually take over and it will push the atoms apart again. So really encourage you to explore this app, but just to understand that everything that holds atoms together or pushes them apart when they get too close is simply a Coulomb force of attraction for bonding or repulsion when they're being pushed apart. And finally, at the bottom of page 58, let's look at electric fields. We'll be looking at two equations in particular. The definition of electric field strength, just E equals F over Q, force divided by charge. And then the electric field strength at a distance d from a point charge q. And you'll see quite easily that we just find that by taking the Coulomb law and cancelling small q. But let's rather go and look first at this wonderful simulation called Charges and Fields from PHET. So let's have a look at this PHET app called Charges and Fields. I'm going to hide my head so we can see all the controls over here. So let's start off by placing a 1 nanocoulomb charge there. That's the charge that creates an electric field. Now, what do we mean by an electric field? Well, we simply mean a region in which the charged particle would experience a force. So here's a test particle, a charge, and we can see that when we put it close to our 1 nanocoulomb charge, it experiences a force which is shown by the arrow. And because this is a positive test charge, the force is away from this positive charge, because we know by now that like charges repel each other. If it gets further away, you can see that the force gets very quickly much smaller. If it gets closer, the force gets very quickly much bigger. So because it's a Coulomb force, that force depends very much on distance. And by moving this around, we could actually almost draw a map of the electric field, because the electric field simply shows the direction of the force which would be experienced by a charged particle. If we mapped all those positions, we could then draw in an electric field and say, right, around this charged particle here, we've got an electric field like this. And wherever I move my test charge, those white arrows, which are the electric field, will show the direction of the force that would be experienced by this test charge. Okay, so that's very simple, just for a single charge. Let's switch off the field and let's see what would happen if we had, for example, a negative charge. We put a negative charge there, and now we can see the direction of the force experienced by the test charge is towards the negative charge. Again, the same thing applies. The closer you get, the bigger the force. The further away, the smaller the force. And again, we could map out an electric field in the area around this charge. And we could then draw the electric field. And as we expect, we'd find that all the arrows point towards the negative charge. And wherever we take this charge, it shows the direction of the force that it would experience. So this is what we mean by an electric field. Now, what we could do, of course, is make it even more complicated. Let's have a negative charge and a positive charge. We're now going to have a more complex electric field between these two charges. Once again, we use our test charge. As we expect, on the left, the force is away from the positive charge. On the right, the force is towards the negative charge. In the middle, we have a very large force because the test charge is being pushed by the positive charge and pulled by the negative charge. So as we expect, the force is directed from positive to negative. What about above and below? And you can see the force that the test charge experiences is a combination of being pushed by the positive charge and being pulled by the negative charge. So once again, we could do an exercise mapping what the shape of the electric field would be at all these different places, and then we can draw in the electric field. So for two charges, a positive and a negative charge, this is the composite electric field that we would see between them. Now, what about if we take away the negative charge and we have two positive charges? What will the field look like then? Now, again, around each positive charge, I think we know exactly what to expect. But what about in between them? In between them, we can reach a point where the field is effectively zero, because the test charge is being pushed from both sides, so it experiences no net force. So a test charge would tend to be pushed out of the middle, upwards on that side, and downwards on that side. So again, we can map the electric field between these two here. And you can see with two positive charges, that is the electric field between them. Isn't this a wonderful simulation? And you can take any field you want. You can add as many charges as you want. You can make the field increasingly complex, and you can look at how the electric field would appear. So teachers, please spend some time investigating this wonderful simulation. You can build any electric field you want, and it's a really good way of understanding electric fields and electric field lines. And this is where our equations ultimately come from. So looking at the equations, if we have a point charge Q and we use a big Q for that, and we go a distance d away from it, then the electric field strength is K Coulomb's constant times Q, that point charge, over R squared. Please notice this only applies to a point charge. If it's an extended charge or a metal plate, then the electric field will be more complicated. So electric field strength from the definition here is the force experienced by a positive unit charge. Where do we get this equation from? we simply substitute Coulomb's law for F there, and you'll see that the two small q's will cancel, giving us E equals KQ over R squared. Now, to finish off with, at the bottom of page 58, we just have some points about electric field strength, and we would have seen these when we looked at the simulation. Number one, E is a vector, and it shows the direction of the force which a positive charge would experience. So please remember it's a vector and needs a direction, particularly when giving your final answers. Secondly, electric field lines are drawn away from a positive charge and towards a negative charge, just like you can see in the diagram here. Thirdly, small q is actually this yellow test charge, which experiences a force in the electric field. And we usually imagine a 1 Coulomb test charge. Whereas big Q in red here represents the point charge, which is responsible for creating the electric field. So don't confuse those two charges. Now, the section we've just done, introducing the equations and the variables, is very important, but you're never going to become skilled in using the equations without actually trying them yourself. Perhaps the best way at this stage is to look at some previous matric papers. So we'll start off with an illustrative exam example. This is not in your booklet, so just concentrate on the screen and watch how I do it, and then you'll get the chance to try 3 recent exam questions for yourself. So as we mentioned, question 7 is usually a long question. On average, it's 18 marks. This particular question was 23 marks. So it's 1/6 of your paper almost. And we're going to look at the September 2020 question, which came from the KZN preparatory exam. Now, it's not in your booklet, as I said, so just concentrate on the screen and learn how to do it. As usual, this was in 2 parts. There was actually a Coulomb calculation, including free body diagrams and forces, and then an electric field calculation. So we're going to leave out 711 and 712, which are really just recall, and look from 713. Let's read the question. An insulated sphere Q of mass 8 times 10 to the minus 2 kilograms. We don't need to draw a picture because the picture is drawn for you in the exam. If necessary, just draw on that. Carrying a charge of plus 6 microcoulombs, plus 0.6, is hung by a string of negligible mass. That means effectively it weighs nothing. Don't consider it in your calculations. Another charged sphere R carrying a charge of minus 0.9 microcoulombs is held a distance of 0.15 meters away, directly to the right of it. So the string makes an angle theta with the vertical. Now, as we're going to see, there are 3 forces on Q. Tension in the string up to the left, electrostatic Coulomb force to the right, the gravitational force directly down. And as always, drawing the correct free body diagram is actually the correct way to handle these. But we also looked at this in video 5, which was all about free body diagrams. And I suggest you look back at that. First question says, draw the free body diagram. As we said, always start with the weight. That's the one that's always there and is always vertically downwards. Then we have the tension force in the string up to the left, and the electrostatic force, we can call it Fe, the Coulomb force of attraction, to the right. And we know it's attraction because we have a positive charge Q and a negative charge R. So that's our free body diagram for sphere Q. Next question says calculate theta. Now what we need is to convert our free body diagram into a triangle of forces. We've kept all of these arrows parallel to where they are, but instead of putting them with their tails together in the free body diagram, we've put them head to tail in the triangle of forces. And we can identify them, and the angle theta is the same angle which is between the string and the vertical. And we know that the weight is vertical. So now it becomes a simple trigonometric calculation. Tan of theta is the electrical force over the weight. So the weight, which is mg, we can do a quick calculation. That's 0.784 newtons, using from our constant sheet the acceleration of gravity. And our electrostatic force, we use Coulomb's law, put in the 2 charges in the distance, we'll get 0.216 newtons. You can try that carefully. And so the tan of theta, we just divide these 2 forces. electrostatic force of 0.216 by the weight force of 0.784, and theta will be 15.4 degrees. Okay, just a reminder again, in a free body diagram, the tails are together, but all the forces are applied to charge Q. But in the triangular forces, you do it head to tail. And it's a closed triangle, which tells you there's no resultant or net force on Q. Let's do 715, calculate the tension in the string. Because we've already drawn the triangular forces, again, it's just a simple trigonometric calculation. Cos of theta is the weight over the tension. Therefore, the tension equals the weight over cos theta. And the weight we've already calculated was 0.784. And theta, 15.4 degrees, was the answer to 714. And that gives you an answer of 0.81 newtons. And of course, you'd expect it to be similar to the weight, because you can see from the triangle, they should be similar forces. So that's 7.1, which is all about triangular forces and a Coulomb's law calculation. 7.2 is completely different. It's an electric field calculation. So please, we must use our electric field law and not our Coulomb law. There's a point charge plus Q is placed a distance d from position P. The field at P due to plus Q is E. Now, please don't think that that's potential energy EP. That's the electric field at P. And we've put a 1 because it's due to the first charge. Once again, this is the second part of the question. It's not in your booklet, so just concentrate on the screen. So we go to our data sheets on page 39, the second page of data sheets at the top, your electrostatics equations. There is the equation for electric field, a distance r, or it's called d here, away from a charge q. So that's simple enough, but then it says when a second positive unknown charge qx, we're going to call it charge 2 to make it simpler, is placed a distance d to the left of plus q. The net field at P, due to the two charges, is now 2E. They're taking a long way to say that the electric field strength doubles at P when you add the second charge. They're telling you if the magnitude of the charge on plus Q is 0.5 microcoulombs, calculate the magnitude of the charge Qx. They don't tell you these distances in meters, but you don't need to know them. You just need to know that charge 1 is 1 distance away, charge 2 is 2 distances away from point P, where the electric field is being measured. So the electric field at P, the total electric field is twice the electric field due to the one charge only. Now, here is the answer from the memo for the exam. And you can see there's a whole lot of writing, and there's only 4 marks for this. And honestly, this is too much writing for 4 marks. And this particular solution actually gave me a headache. So let me propose a simpler solution than the one in the memo. So here we go. So we've said basically when you add a second charge number 2, the total electric field becomes twice what it was when you just had 1 charge. So total electric field is the electric field due to charge 1 and electric field due to charge 2. Remember, the P is just telling us that's the electric field measured at P. Please don't confuse with potential energy. But we were also told that it was double the electric field when there was only 1 charge. So we can say the electric field at P due to charge 2, do a quick calculation, we'll find actually it must be the same as that due to charge 1. Obviously, because it's doubled, you've just added the same again. Now, we would expect that charge Qx must be much greater than plus Q, because it gives the same electric field at P, even though it's double the distance away. So all that's left is to calculate what that charge is. So we use our equation for electric field strength, kq over d squared. The reason we put in 2d for this charge, which is in blue so you can see it clearly, is because it's 2 distances away. And remember, we don't write 2d squared, we write 2d in brackets, all squared. So when you calculate that, your d's will cancel, your k's will cancel, and you'll come up with the fact that charge q2 must be 4 times the size of charge q1. We knew it had to be bigger. So it's 4 times the magnitude of Q1, which you were given, 0.5 microcoulombs, and 4 times 0.5 is 2. The magnitude of charge Qx is 2 times 10 to the minus 6 coulomb. And I think you'll agree that this is an easier way to visualize it than the answer which was given in the memo. So it's time to try some examples from some of your recent matric papers. Question 7 is a long question. It averages 18 marks. You're going to take about 20 minutes on it when you do your paper. So it's not one you can rush through quickly. It usually has 2 distinct parts. And if you look at these last 3 years, in 2018, first part was around charge conservation. The second part, a Coulomb and electric field calculation. Here you can see a 2-dimensional arrangement of charges, not just in a straight line. 2019, similar to the illustrative example we've just looked at, there was a Coulomb calculation with a triangle of forces, needing a free body diagram, and a straight linear electric field calculation. 2020, again, a Coulomb and electric field calculation for 2 charges in a straight line and a point beyond them. And then again, a 2-dimensional arrangement of charges with a Coulomb calculation. So let's have a look at these. Now, of course, as I always say, I would like you to pause or stop the video here for 48 minutes. That's the time needed to complete 3 times 16 marks while you try to complete the questions. These questions are found on page 59 to 61. Now, of course, that's a lot of time, so you might prefer to do them one at a time, then give yourself about 20 minutes to try each one first. I really must encourage you to try the problems first. If you just watch the answer, you will learn very little, and you may as well just go straight to the menu. So please pause or stop the video here and try the problems yourself. Right, so let's start with November 2018. This was a long question for 19 marks, quite a few different parts. So 3 small identical metal spheres. They're on insulated stands to make sure that they can hold a charge. They're initially neutral, and then they're charged to carry these charges, minus 15 nanocoulombs, an unknown charge Q, which of course you're going to have to calculate, and plus 2 nanocoulombs. Remember we said that 1 coulomb is a very large charge, and you will almost never encounter that in nature. You're told for the first part, the charge spheres are brought together so that they all touch each other at the same time, and they're then separated. The charge on each sphere after separation is minus 3 nanocoulombs. And of course, you're asked to calculate Q and then draw an electric field pattern. Let's go through it slowly. So before they touch, these are the charges. I know they're in nanocoulombs, but just to make things easier, I've just put minus 15 Q and plus 2, but we understand those are in nanocoulombs. The red part of the question, they all touch together so that the charge will be shared. So while they're touching, the combined charge will be minus 15 plus Q plus 2. Then they're separated, and we're told after separation, the charge on each sphere is minus 3 nanocoulombs. Now you're asked to calculate Q, but remember this combined charge is split 3 ways. So we can take the combined charge divided by 3, and that must be equal to any of the individual charges. So a simple equation, and you can solve that with some basic mathematics, and you'll get an answer of plus 4, and of course it's plus 4 nanocoulombs, plus 4 times 10 to the minus 9 coulombs. Not too difficult. Then you're asked to draw the electric field pattern associated with S and T after they're separated and returned to their original positions. Now, after they're separated, we're told the charge on each is minus 3 nanocoulombs, and they're a certain distance apart. Now, of course, we worked with the PHET simulation for charges on fields. 2 negative charges would have this sort of electric field. And I encourage you to go to the simulation and try to set it up for yourself. All the arrows pointing towards the negative charges, because remember, the arrows indicate the direction of the force on a positive test charge. Of course, you're not going to draw lots of arrows. Here's the picture from the memo that they'd like you to draw. And here's how the 3 marks were allocated. 1 for the correct shape, one for the correct direction towards each negative charge, and one saying that the lines must not cross and they must touch the spheres. Now I'm going to jump to 7.6 because there's a more complicated calculation in the middle, and this one is not too difficult. One of the charged spheres, either P or T, experienced a very small increase in mass after it was charged initially. Now that word initially caused some problems and made an ambiguous answer. 761, which sphere, P or T, experienced a small increase in mass? Well, immediately I would say P, and that is a correct answer because it went from neutral to minus 15. So it must have gained electrons because that's the only way charge is transferred, by the gain or loss of electrons. Look at S. S would have lost electrons, so its mass would have gone down slightly. But in the memo, they also accepted T because that word initially is ambiguous. And in fact, T gets charged from +2 to -3, so it must have gained electrons in that part of the process. So actually, you could answer for either of these, but I'm going to continue with P. Calculate the increase in mass by the sphere in question 761. Well, first of all, let's calculate how many electrons did P gain to get a charge of -15 nanocoulombs. Number of electrons is the charge gained divided by the charge on the electrons, which you just get from your constant sheet. So -15 times 10 to the -9, the amount of coulombs, that's the charge. The charge on the electron from your constant sheet on page 40, minus 1.6 times 10 to the -19. Now, please make sure that you know how to put these numbers into your calculators, especially with two minus signs. It can be confusing. The answer 9.38 times 10 to the 10, there's no units because it's simply a number. That's the number of electrons, and that's about 100 billion electrons, so a very large number indeed. Now, what was the mass gained? Well, it's the number of electrons, 9.38 times 10 to the 10, times the mass on the electron, which is also from your constant sheet on page 40. Again, lots of exponents to deal with, and an answer of 8.55 times 10 to the -20 kilograms. That is an incredibly small mass, and certainly not detectable with a scale. Now, moving to the middle numbers, 7.3 is a recall question. We dealt with that right at the beginning. We're not going to look at that again. Calculate the magnitude. Please notice this word. Normally for force and field, you need to give a direction, but they only ask for the magnitude. So don't waste your time offering a direction. So you're told these spheres, each with the same charge of -3 times 10 to the -9 coulombs, are now placed at these points here. We've got a two-dimensional arrangement. Fortunately, they are at right angles to each other. And you're asked to calculate the electrostatic force on P and the net electric field at the origin. Now remember, we're going to go to page 39, the second page on our data sheets, look at the electrostatics equations. Obviously, for force, we're going to take Coulomb's law, which is there. For electric field, it could be one of these two, but always go simpler if you can. And you're going to see that the simpler definition, electric field strength equals force over charge, is in fact the one which we are going to use. So let's have a look at the situation. So first of all, please notice there will be a force exerted by S on P. It's a repulsive force because all charges are negative and two negative charges repel each other. So it will be in a downward direction. Secondly, there'll be a force exerted by T on P, we'll call FTP. Again, because it's repulsive, it will be a force to the left. We're indicating the directions of the force on P. Those two forces will combine to give you a net force, which will be in that direction. Now, we don't need to give the direction, just the magnitude, and we can simply use Pythagoras to find the net force once we've calculated those two. So it's a bit of a tedious calculation, but it's not difficult. We'll simply use Coulomb's law. Make sure you write down the equation to calculate force. First of all, the blue force exerted by S on P. K Coulomb's constant. All the charges are the same. We don't need to put in minus because we're just looking at the magnitude of the force, and the distance between S and P is 0.1 meters. Do it carefully on your calculator, and we get a force of 8.1 times 10 to the minus 6 newtons downwards. Same story for the force exerted by T on P. The main difference is the distance is much bigger. It's now 0.3, and we get a force of 9 times 10 to the minus 7 newtons to the left. Might be useful to make it 0.9 times 10 to the minus 6, so your two forces have the same exponent. Then we just use Pythagoras' theorem, F net squared is equal to FSP squared plus FTP squared. So therefore, F net is the square root of the sum of the squares. Put in your numbers, carefully use your calculator, and we'll get a net force of 8.15 times 10 to the minus 6 newtons. And again, you can check, this should be of a very similar size to these forces here. It's just the magnitude of the net electrostatic force. In the last part, the magnitude of the net electric field at the origin. Now, because they asked you for the force in part 7.4, it's quite likely that you're going to use that. And there's our answer. The net force from 7.4 is 8.15 times 10 to the minus 6 newtons. We also told that all charges are minus 3 times 10 to the minus 9 coulombs. So it's a very simple calculation. Electric field strength at the origin is the force experienced by charge P divided by the quantity of charge. Force was 8.15 times 10 to the minus 6. Charge was 3 times 10 to the minus 9. Again, we're not worried about direction, so we don't put in the negative. And your calculator will give you the answer of 2.72 times 10 to the 3 newtons per coulomb. So again, go with the simplest equation. Otherwise, you have to do two calculations together. Now, do you remember on page 5, we have these skills which are required for physical science. And at the beginning of this video, we highlighted those. And I want you to see scientific notation. You've certainly used that a lot, haven't you? And so many students fall short on this electrostatic question because they just can't correctly convert numbers and put them into their calculator. Please make sure that's not you. Also need to be able to convert units and know about milli, nano, micro, and so on. Change the subject of the formula and some basic trigonometry skills. And in fact, we could add to that Pythagoras' theorem, which we've just used in the last calculation. So please, this is a skills-based series. Work on these skills so that you can answer question 7 correctly. Let's take a look at question 7 from the November 2019 final matric exam, paper 1. Now, as always, this is a long question. It was 18 marks and in 2 parts. The first part, a Coulomb's law calculation with free body diagrams and a bit of trigonometry. And the second part, an electric field calculation. You're given a nice drawing in the exam, so there's no need to redraw this. Just use their drawing and add to it. You're told that a small sphere Y carrying an unknown charge is suspended at the end of a thin light string attached to a fixed point like the roof. Another sphere X carrying a charge of 6 times 10 to the minus 6 coulombs is on an insulated stand and it's brought close. Sphere Y experiences an electrostatic force, which must be repulsion because they're not attracting each other, comes to rest 0.2 meters away from sphere X, the string with an angle of 10 degrees as shown in the diagram below. Now you do need to read the question, but it takes a long time to read it. And all that information is actually summarized in the drawing. So once you've read it once, just look at the drawing. First question for 1 mark, very easy. What is the nature of the charge on sphere Y? Is it positive or negative? Well, it has to be positive because Y is being repelled by X, and we're told that X is positive. Secondly, calculate the magnitude of the charge on sphere Y if the electrostatic force is 3.05 newtons. That's quite simple, and just use Coulomb's law and substitute in what we know. We know the force 3.05, that is something that is given. The constant, Coulomb's constant 9 times 10 to the 9 is obvious. Charge X is also given, 6 times 10 to the minus 6. and Q is the charge on Y, which is unknown, and the distance of 0.2 meters is also given. So it's just a case of putting in the numbers. Notice you've got a positive exponent and a negative exponent. Very easy to get confused. So put these numbers in carefully, do the calculation, and solving for Q, we get Q equals 2,26 microcoulombs times 10 to the minus 6 coulombs. And you can see where 1, 2, 3 marks are allocated there. Nothing too difficult so far. Now you're asked to draw a labeled free body diagram for sphere Y, and you'll use this to calculate the magnitude of the tension force in the string. So we do quite a lot of this in video number 5 on free body diagrams. I encourage you to refer to it again. Drawing the free body diagram, always start with the weight, because that's always vertically downwards. Then the tension is obvious because it's upwards along the string. Remember, a string can't push, it can only pull with a tension force. The third force is, of course, Fe, the electrostatic force directed away from X or to the left. So that would be 3 marks for 3 correctly labeled arrows. It doesn't matter how long they are. You do not have to draw them to scale. And my drawing is definitely not to scale. 714, calculate the magnitude of the tension in the string. We need to take that free body diagram and convert it to a triangle of forces. Now, if that confuses you, look at this carefully. In the free body diagram, all of the arrows have their tails together, and their tails are attached to the body, to Y. When we do the triangle of forces, we add the arrows head to tail. We add them one after another in succession, and we get a closed triangle, which indicates that there's no resultant force acting on body Y. You can do it in a slightly different arrangement, but because the 10 degrees was between the string and the vertical, and because the weight is vertical, it makes sense to do it this way. If you're not sure how I converted a free body diagram to a triangle of forces vector diagram, please discuss this with your teacher. Then it's just a bit of trigonometry. We know that sine theta is the electrostatic force over the tension force. All 3 of these are forces. So therefore, T is equal to the electrostatic force over sine theta, 10 degrees. Now, the electrostatic force was given to us as 3.05 newtons divided by sine 10, and we get a tension force of 17.56 newtons. Now read the question carefully. It asks for the magnitude, so you don't need to worry or to specify a direction, and it's only 3 marks. So that's the first part of the question, to do with Coulomb's law. Second part, 7.2, is an electric field calculation. You're told that 2 small charged spheres, A and B, are in insulated stands as usual. You're told how much each charge is, and they're placed 0.4 meters apart, as shown in the diagram below. M is the midpoint between the spheres. So obviously from A to M is 0.2 meters. Now, once again, all of that writing is summarized in the diagram they give you. So make use of that diagram. 721, define the term electric field at the point. That is a recall question. I'll leave that for you to do. You are asked to calculate the net electric field at point M. It's worth 6 marks, so you can expect it to be a calculation with more than one part to it. Now, it's always good to choose a direction for positive. I would suggest you always take up as positive or to the right. In other words, north or east. I think stick to that. It'll just be much easier. Remember, electric field is a vector, so direction must be given. Now, it's interesting to actually set up this field in the PHET simulation, and that tells us that actually the electric field at the midpoint will be directed to the right. Remember, the electric field direction is the direction of the force experienced by a small positive test charge. Obviously, it'll be pushed to the right by the positive charge, and it'll be pulled to the right by the negative charge. Let's have a look at that quickly. So here I am. I've launched the PHET app called Charges and Fields. Again, you know that you have this. So we're going to try to set up the situation just as it is. And of course, we've got a positive charge on the left-hand side. We've got a negative charge on the right. I'm going to put in 2 charges because in fact it's twice the size of the positive charge. Now we use our test charge to investigate the electric field, and you can see between those two, we'd have a very strong electric field towards the right. Now, if I took away the positive charge, we'd still have an electric field to the right. And if I took away the negative charges, we'd also still have an electric field to the right. So what these charges are doing is simply strengthening each other. And if I draw in the electric field here, you can see indeed we can expect to get quite a large value of electric field from the midpoint M, and definitely directed to the right. So this just helps us to know what to expect and also to visualize the problem. If you're just plugging numbers into equations, often you can lose your way and lose the conceptual understanding. So how do we do this? Well, our main equation we're going to use from page 39, your data sheets, is just E equals KQ over R squared, electric field strength, the distance R from a charge Q. Now, remember, the electric field at M has two components, one from charge A and one from charge B. Both of them will be to the right, so we can simply add them. And please notice that, of course, because M is at the midpoint, the distance between M and each charge will be 0.2 meters and not 0.4. So the electric field at M due to A is simply calculated. K, the constant, is the same. That charge 2 times 10 to the minus 5 is charge A, and 0.2 is the distance. We'll get 4.5 times 10 to the 6 newtons per coulomb. Due to B, same story, we just now plug in 4 times 10 to the minus 5. Notice we don't worry about the minus sign because we know that both electric fields are to the right. Distance is the same, and we get a figure that's exactly double that figure because, of course, this charge is twice as big as that one, ignoring the sign. So we can simply add these because we know that both vectors are to the right. 4.5 plus 9 equals 13.5 times 10 to the 6, or 1.35 times 10 to the 7 newtons per coulomb to the right. How was it marked? One mark for getting the correct equation. Second mark for substituting in the correct figures for charge A. Third mark substituting in correctly for charge B. A fourth mark for adding the two correctly. A fifth mark for the numerical answer. And a final mark for the direction. Please don't forget the direction. For our last example, let's look at the November 2020 question 7. Again, it was quite a long question for 17 marks. And again, two parts. In this question, you first of all have an electric field calculation and then a Coulomb's law calculation. So the usual story, two small charged spheres on insulated stands. They're 0.2 meters apart. The charges are given, and they've given you a very nice picture which summarizes all the information that's written above. M is a point 0.1 meters to the right of sphere B. Now calculate the number of electrons in excess on sphere A, similar to the 2018 question. Calculate the magnitude of the electrostatic force exerted by A on B. And then 7.4, calculate the magnitude of the net electric field at point M. Let's do them one at a time. Remember, our equations we find on page 39. We're going to use that equation. Number of electrons equals total charge over charge on one electron. We're going to use Coulomb's law, and we're going to use this equation for electric field, a distance r from a charge q. These are on page 39. Please remember our progress method that you were taught on page 37. Go back and revise if you've forgotten it. Good to draw a picture, but a very good picture is given in the exam, so there's no need to do that. You can just draw on their picture. Work out what is required, which we've highlighted in green. Look for what's obvious, things like K, the Coulomb constant. Check carefully what is given that I've highlighted in red, and then relate these by choosing the correct equation, as we've done above here. Substitute and solve. So first of all, calculate the number of electrons on sphere A. Now, it's only 3 marks, so we don't need to follow the whole progress method, but that's what's required. So we're going to use this equation. The charge is what was given, minus 4 times 10 to the minus 6. Charge on the electron is obvious. It's on your constant sheet. And we simply divide and get 2.5 times 10 to the minus 13 electrons. There's no unit. It's simply a number. These negative signs are not really important because we're just calculating the number of charges. Secondly, the magnitude of the electrostatic force exerted by A on B. We simply take Coulomb's law, force exerted by A on B, K Q1 Q2 over R squared. K is obvious, the constant. Charge Q1 is given to you. Charge Q2 is also given, and we divide by the distance in meters squared. Notice no sign is given to the charges, because you simply asked to calculate the magnitude. You should know that these two would be attracted to each other because we have a negative and a positive charge. Answer 2.7 newtons. Now, if they did ask for the direction, which they haven't, magnitude of the force exerted by A on B, you would say to the left, because the force on B would be to the left towards A. Calculate the magnitude of the electric field at point M. Now, just like I did in the last one, it's quite interesting to set this up on the PHET simulation for charges and fields. And we have a negative charge, we have a positive charge of a similar value, -4 and +3 microcoulombs. And if we put our test charge here, we would certainly expect that the electric field would be directed to the right, simply because it's closest to the positive charge that will repel it, and it's quite far from the negative charge that would attract it. So we expect this influence to be greater. But you just asked for the magnitude. So notice this is 5 marks. In the previous question, it would have been 6 marks. I'm not going to set up this again in PHET, but you can do that. So remember again, the electric field at point M has a component from charge A and a component from charge B. So let's calculate the magnitude of the net electric field. This is our main equation, which we get from page 39. We're remembering the two components of the electric field, and we calculate each separately. The electric field at M due to A, KQ over R squared, substitute the values. Please remember the distance is 0.2 plus 0.1, which is 0.3 all squared. Very important. And we get a value of 4.0 times 10 to the 5 newtons per coulomb to the left, because this was a negative charge. Electric field at M due to charge B, same story, except the distance is now only 0.1. And we get an electric field of 2.7 times 10 to the 6 newtons per coulomb to the right. Notice that this is about 10 times larger than this, because it's 10 to the 6 as opposed to 10 to the 5. Now, again, we're going to specify that to the right is positive. So when we add up the two electric fields, we'll take EAM as negative because it was to the left. We'll take EBM as positive because it's to the right. And when you add those two correctly, we get a final answer of 2.3 times 10 to the 6 newtons per coulomb to the right. Now, they take charges A and B, and we now have an interesting system where another charge D is added, and they're arranged on a rectangular system of axes as shown. Now, both these pictures are given, but I just repeat this picture because we need to know the value of the charges on A and B. Net electrostatic force experienced by sphere A is 7.69 newtons in the direction as shown. Again, everything you need is given on these drawings. Don't redraw them, but just pay attention to them. First, a simple question, is the charge on D positive or negative? It must be positive because we're told that this is pulled in an upward direction. We know that A is negative. It's pulled towards B, which is positive, but it must also be pulled towards D. Otherwise, the resultant would be in a downward direction. Now, calculate the magnitude of the charge on sphere D. Now, I have to say, I think this is quite a tough question for just 3 marks. And it really requires you to think about it carefully. So let me try to make it clearer. You're not given any direction. for this resultant force. But we are told that the net force is 7.69 newtons. You do know that the force exerted by A on B is 2.7 newtons, but you calculated that in question 7.2. So you're carrying it forward. The fact that this is so few marks means you should look out for an answer carried forward from a previous sub-question. Now, obviously, there's also a force on A exerted by D, but we don't know the value of that, and we don't know the charge on D. So we're going to calculate that force first from the other two, and then use that to find the charge on D. So all we can do here is use Pythagoras, because these two forces are at right angles. So we can say F net squared, the hypotenuse, equals FAD squared plus FAB squared. Now just rearranging that, putting in the numbers you were given, 7.69 for F net, we calculated 2.7 for FAB, and just solving for FAD, we get 7.2 newtons. So that is the force exerted on A by D. Now we use Coulomb's law to simply say the force exerted on A by D is KQ1 Q2 over R squared. K is your constant. Q1, we can see from here, is 4 times 10 to the minus 6. Don't worry about the sign. Times Q, the unknown charge over the distance, 0.15 meters squared. And that's equal to the resultant force AD, which is 7.2. Sorry, not the resultant force, force exerted on A by D. Do the calculation, solve for Q, and you get Q, the charge on D, is 4.5 times 10 to the minus 6 coulombs. Now, I think they were very stingy with marks here. You can see you get just 1 mark for that Pythagoras equation. You get 1 mark for substituting incorrectly into Coulomb's law, and 1 mark for the final answer. So that was quite a tough one, and you'd have to have worked really fast to complete all of that in 2 minutes. So this was quite a long video, and electrostatics has long questions and can be quite complicated. There are many different formulae, calculations involve complicated scientific notation. So please spend some time, particularly as this is not matric work and it needs some revision. But the way to tackle question 7 is to break it down into smaller parts, and then I believe you will find it manageable. That's all for this video. If you're interested, there's a 25-minute video about lightning as an electrostatic phenomenon. This is not strictly in your syllabus, but if you'd like to understand more about how lightning works, why don't you watch this now? It's included with the short section videos.